Alright, so today we're going to be doing probability of compound events. Okay? So, we have a lot of vocabulary to cover today. Oh, okay, yeah, there's one on the board. So, the probability is the numerical measure of the likelihood that something will occur. And the range of probability is always between 0 and 1. So, it could either be 0 to 100% or 0 to 1 as represented by a fraction or a decimal. So if something is impossible, it's going to have a probability of 0. If something is completely certain to happen, it's going to have a probability of 1. And if something is as equally likely to happen or not happen, it has a probability of 50% or 1/2. Everything else in probability falls within that range. So if your number is outside of 100%, like beyond 100%, or a number bigger than 1, it is not a probability anymore. If it's negative, it's also not a probability. Now, a trial is a single random action done in anticipation of a result. Outcome is the result of the trial. The sample space is the set of all possible outcomes. So the sample space isn't actually what happens, it's what can happen. So there is a difference between those two. And the experiment is the collection of the trials. So it's just multiple trials being collected. So let's say I tossed a coin once. There's really only two things that can happen, right? Heads or tails. Correct. If I toss a coin twice, there's 4 things that can happen. Heads, heads, tails, tails, heads, tails, or tails, heads. And the more I toss the coin, the more chain of different events can happen, right? You could do heads, tails, heads, tails, head, tails. More and more possibilities open up. That's why it's less likely that you get 6 heads in a row versus just 1. Okay.
That's why they say it's like flip a coin 10 times. It's most likely to get 5 heads, 5 tails, because there's the most amount of ways it can pull up. It can help come out.
Exactly. Yeah. So a simple event is when only one possible outcome exists, and a compound event is when more than one outcome exists. So and or. So I want to just address these possibilities right here at the bottom because they do come up on the homework. So I'm going to have you add this in. If it's an or problem, you're going to use addition. And problem, you're going to use multiplication. And then you also use multiplication, but you also reduce consecutive denominator. So it all makes sense when I'm talking about when we actually go to do it. So that's just like a little note to help you when the time comes to remember what operation you're going to use. Okay. So we're going to do a lot of ors, and then we have a few ands and thens on the homework that I'm going to do one example of, so you've seen it all. Now, while you write that down, I'm just going to talk a little bit about the difference between mutually exclusive and inclusive. So mutually exclusive events are 2 events that don't affect each other at all. That's like me flipping a coin and rolling a die. The chances of those 2 things have no overlap. A mutually inclusive event is where an event has a shared outcome, an overlapping outcome. That could be like the chance of picking a king or a spade, because there is a king of spades. So there is an overlap between those 2 events happening. Okay, so we're going to do examples of both those scenarios as well. Inclusive events and whatnot have their own rules and whatnot, so we'll talk about that. Alright, so let's go ahead and do some examples. So let's talk about the probability of an event happening. These are mutually exclusive events, okay? And these are ors. You see the word or is used, which means that it's going to be addition, okay? So what is the probability of drawing a king or queen? So out of a standard deck of 52 cards, how many kings are in a standard deck of cards? 4. Plus, how many queens are in a standard deck of cards?
4.
Also 4. And is there ever a chance where you can get a king or queen on the same draw? Picking one card?
No.
No. So the chance of that happening is 8 out of 52, because you're okay with any of those 8 cards. So to get this, you just do 8 divided by 52 times 100, which will give you approximately 15.4%. chance of happening. Alright, the next one says a stack of baseball, hockey, and basketball cards are shuffled face down. What is the probability of randomly selecting baseball or hockey from the stack? Can you select one card that is both baseball and hockey at the same time? No, so this is mutually exclusive. So how many total cards are there here?
30.
Good. And how many of those cards are baseball cards?
5.
Good. So the chance of picking a baseball card is 5 out of 30. Plus, you're also okay with picking what kind of card? Hockey, which is how many?
10.
So if I add these together, I get
15 out of 30, which is 1/2.
which is 1/2. Which makes sense because half of the cards we have are baseball and hockey, correct? Those represent half of the stack. So do we have any questions about that form of probability? A lot of probability you've also probably seen in passing on your own, like through life. And it is a little bit intuitive as well, some of it. So now we're going to talk a little bit about inclusive events. So inclusive events are also another type of OR event, and we also use the AND probability. So I'm going to talk a little bit about how that works. So what is the probability of drawing a king or a diamond from a standard deck of 52 cards? How many kings are there in the stack?
4.
Good. How many diamonds are there? Anyone know how many of each suit? 13. Now that would be the answer, but we do have an issue. Is there a possibility of getting a king and a diamond on the same card?
Yes.
Yes. And how many king of diamonds are there in the deck?
1.
Just 1. We have to subtract that away because I'm going to explain to you why. This 4 out of 52 represents the 4 kings in the deck. Spades, clubs, hearts, and diamonds, correct? This 13 out of 52 represents all of the diamonds in the deck, which is 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. So didn't we count the king, thank you, of diamonds already twice? So we have to subtract away that double count, okay? So if we do that math, that's going to come out to be 16 out of 52, which is 31%, approximately. All right. In a school with 1,000 students, 550 take Spanish, 650 take biology, and 300 take both. What is the chance that if you pick a random student, they take either Spanish or biology?
Spanish plus biology.
Yeah, basically. So you're going to do the chance of Spanish plus the chance of biology. But if I do this math, this comes out to be 1,200 over 1,000.
What do you mean in a school of 1,000 students?
Well, that's where I'm trying to get to.
So
what's the issue?
Overlap.
Oh, yeah,
Yes, they overlap. So I just want to show you something that tells you right off the bat that there's an overlap. This is bigger than 1. Probability can't be bigger than 1. This is a high indicator that we double counted. So we need to subtract away 300 over 1,000. Because we've double counted all those students who take both Spanish and biology. We counted them again and again. You can't double count. That gives you 900 over 1,000, which is
90%.
90%. Does anyone have any questions about that? So this could also be set up in the form of a Venn diagram, correct? If you wanted to, you don't have to draw this. I'm just going to kind of show you to refresh your memory. You have a Venn diagram. This would be the students who take both, 300, which would mean you'd have to do 550 minus 300, so what, 250? And over here you'd have to do 350. And then on the outside would be the students who didn't take anything, and so on. So same idea of what you did with the Venn diagrams. Now we're just doing it using a different operation.
So when it says 550 take Spanish and 650 take biology, then 300 students take both.
That means,
Alright.
so how will we know if it doesn't say a bunch of people take both? Like,
Well, I'd have to tell you.
okay.
Yeah, you have to be given a certain amount of information to be able to calculate these things. Okay. So this question says we have a spinner that has 20 equal size section. Why is it so important that they tell me that these are equally sized?
In order not to change the probability of each one happening.
Yeah, if they weren't equally sized, like you both said, they would have different probabilities, correct? If you think of any game show that uses either a spinning wheel or anything like that, what do you notice about those sections?
Really good ones are very small.
Yeah, the ones that win a lot of money are really small because it reduces the chance of them occurring, right? So most game shows are not going to use these kind of wheels where everything's equally as likely, correct? So I just want you to keep that in mind. There is more advanced types of probabilities that involve these questions, but we're going to keep it simple with everything being equally likely, to start it out. So, the probability of spinning a 2 or a 5. Is there ever a chance where you can spin something once that is both a 2 and a 5?
No.
No.
So these events don't overlap, which means they are mutually exclusive. These are mutually exclusive events, okay? So, what is the chance of spinning a 2?
2 out of 20.
1 out of
20.
1 out of 20.
which is 5%.
5%.
Plus, we're also okay with getting a,
1, 5, which is 1 out of 20.
which gives me
1 out of 10,
a, 1 out of 10, which
or
is
10%.
10% chance. Each one of these represents 5% chance. So each one that you add into the situation is going to be an additional 5% chance. Now, what is the probability of spinning a multiple of 2 or 5? Is there a way that you can spin a number and receive a number that is both a multiple of 2 and 5?
Yes.
Yes.
10, what else?
20.
20. Exactly. So there's two numbers that are what we would call mutually inclusive or inclusive. But there are some that are separate, right? Like 8 would be a multiple of 2 but not a multiple of 5. 15 would be a multiple of 5 but not 2. So there are some that are mutually exclusive, but overall, it's an inclusive problem, correct? So if you have one example of inclusion, your whole problem is inclusion. Does that make sense? All right. So, what are the odds of just spinning a multiple of 2? Well, we got 2, 4, 6, 8, 10.
Yeah, so 50%.
Oh.
10 out of 20. Now, we don't want to convert to percents right away, but yes, you were right.
Right.
Plus, how many of those are multiples of 5?
4.
4, because we got 5, 10, 15, and 20. And how many of those are both multiples of both of the numbers? Just 2. It would be 10 and 20, correct? So if that's hard for you, you can feel free to write them all out as well. So this is a 60% chance. So the odds are pretty high for that one. Considering the 2 alone is 50%, exactly. So do we have any questions about this one? All right. Now we're just going to talk about the complement. The complement is pretty easy to understand once you get the hang of it. If I told you I was going to give you $100 if you have 2 choices to pick from. You have a die that lands on anything except for a 2, or the die lands on the 2. Which one are you going to go for?
Anything but the 2.
Right. You know these things intuitively, right? I don't have to explain to you why the probability is the way it is. What is the chance of rolling anything but a 2?
Pretty high.
5 out of 6. Exactly.
Am I wrong?
What is the chance of rolling a specifically a 2?
1 out of
Pretty
6.
handful.
1 out of 6. What is 5 out of 6 plus 1 out of 6?
6 out of 6.
Which is?
100%.
Which is also known as 1, correct? So that's why we use 1 in the complement. The complement of something happening and it happening will always sum to be 1. So if you take 1 minus the thing happening, it's going to give you the complement. Does that make sense? Okay. So what is the probability of not drawing a king or queen from a standard deck of cards? wouldn't it be easier to instead try to calculate all the probabilities of the other things happening to just do 1 minus the thing not happening? So didn't we already do the probability of drawing a king or queen?
Yes.
And we got it to be?
8 out of 52.
Good. So 1 minus 8 out of 52. And if you do that as a percentage, you get 84.6. Now what you're going to notice is earlier we got 15.4 for the king or queen. Don't those add up to 100, the probability total? That's because they are complements of each other. Complements of each other in probability will add up to be 100% or 1 in a fraction form. So what I want you to do now is I'm actually going to go through a few of the homework problems with you to get started. Before you start, I'm actually going to just leave it up. So I have your homework problems here. Only 2 through 3, 2, 3, and 4. Number 1 you got. That one's easy. So I want to talk a little bit about the and, because we didn't do too many and examples in the notes, so I just want to mention it. So you roll a blue die and a red die, find each probability. So we want a blue even and a red even. So and is more of a selection process, right? Yeah, because if I need both things to it's not like I'm saying this or this, I need them both to happen at the same time simultaneously. So that's going to be a smaller chance. So we actually use multiplication in that case. Do you remember in the beginning how I said use multiplication for and? So what is the chance of getting a blue even?
3 out of 6.
3 out of 6, because 3 of those 6 sides are even. Times, what is the chance of getting a red even?
3 out of 6.
Also 3 out of 6.
Which is just 1/2 times 1/2, which is 1/4.
1/4.
Okay, so I'm not going to do all those problems with you, but I just wanted to get you started with how to do it. And then to mention, a lot of people were asking me about this, a red less than 7. How many of those sides are less than 7?
All of them.
6 out of 6, yeah. Times, a blue 4 is 1 out of 6, correct? So that's how you do it. Alright, now let's look at number 3. You could cross cancel and you'd get 1/6. Or you could multiply across and simplify. So you randomly choose a tile from a bag containing 2 A's, 3 B's, and 4 C's. How many total letters is that? 9. So you place the tile back. This is really important. When you place the tile back in the bag, that means that you're resetting it back to normal each time. So what's the chance of getting an A and an A? So what's the chance of getting an A?
2 out of 9.
Good. And then to do it again, it's also 2 out of 9.
2 out of 9.
That's how you do it. All right.
Oh, that makes sense.
And then this one is a little bit different, okay? This is a then situation. So let me explain what a then situation is. Then means you did one thing, then you did the next. It's like time has passed, okay? So unlike with the problem we did in number 3, you're not replacing the coins back to their standard position. You're taking that coin and it's gone now, okay? So we have to think about how that affects the denominator. So first and foremost, this part's simple. What is the chance of picking a dime if you had these coins in a bag?
3 out of 9.
3 out of 9.
Oh, I see.
Times, then we want to pick a nickel. We're not putting the dime back into the stack. So how many coins are there left to pick from?
8.
8. And how many of them are nickels?
3.
3. Because we didn't pick a nickel earlier. If we had picked a nickel earlier, that would have depleted, but it didn't. So that's your probability. 9 out of...
Did you get 8?
So this is like, imagine we had a bag of these 9 coins. You picked a dime the first pick. How many coins are now in the bag for the second pick?
8.
Does that make sense? So that's how a then problem has variance.
Do you want to do percentages or percentages?
You're going to do them as percentages. I just was showing you how to get started. All right, so you guys, you're going to want to give me these answers in percentages, but you guys got the rest of the period to work on the homework.